We're going to look at Chapter 2, Counting Methods, Chapter 2, Section 2.2, Solving Problems that Involve Permutations. In this lesson, we'll look at how to understand permutations and understand factorials and factorial notation. If you recall the fundamental counting principle, if there are A ways to perform one task and B ways to perform another task, then there are A times B ways of performing both. For example, Josie has 3 different color sweaters and 3 different color jeans. How many outfits can she make? With the 3 sweaters and the 3 jeans, for each sweater, she has 3 different choices in jeans, which makes 9 options. We could also look at this as a tree diagram. For each type of sweater, we have 3 different types of jeans, which we could see as 9 combinations. Tree diagrams are useful when the number of combinations are small. How many different types of meal combos are there if you can select from 4 types of burgers, 2 types of sides, and 5 different beverages? And that would be 40 meal combos. For each burger, I can select 2 beverages, and for each of those beverages, then I can select for each of those sides, I can select 5 beverages. How many different arrangements of the letters of the word snack? Well, of course, there's 5 options to go in the first position. That leaves 4 for the second position, 3 for the third position, 2 for the fourth position, and only 1 letter left, which is equal to 120 different options. What if the first letter must be an S or an N? Therefore, we only have 2 options. That this must be an S or it must be an N. Right here in the first position. So there's 2 options to go here. Once we place the S or the N in that first position, then there are 4 options to go here, and then 3, 2, and then 1. This would give us 48 different arrangements. A permutation, the arrangement of distinguishable objects in a definite order. For example, Ace, Bob, Cat, Don, and Eric are in line to get a milk. How many different line formations can they form? So if Ace is first, and then Bob, and then Cat, Don, and then Eric, that is a different line order than if Bob was first, and then Ace, then Cat, Don, and Eric. We look to see, for the first position in line, there are 5 options. The second position, there are 4. The third position, there are 3. The fourth position, there are 2 options. And of course, in the last position, there's only 1 option, which would give us 120 different options for them to stand in line. Factorial notation. So this 5 times 4 times 3 times 2 times 1 can be represented by 5 factorial. A factorial is a concise representation of the product of consecutive descending natural numbers. For example, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5,040. Most calculators have a factorial button. It's an exclamation point. Evaluating factorial expressions. So this could pop up on the multiple choice portion. Also, it's going to help later in simplifying combinations and permutations. We see we have 8 factorial over 6 factorial times 2 factorial. As you can see, we have 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You can see that these are the same. They're both 6 factorial. We can cancel those out. It's not necessary to write the complete numbers out. And then we only have 8 times 7 and 2 times 1, which is 28. And the next example in B, we have 12 factorial over 9 factorial times 3 factorial. Well, 9 factorial is embedded in 12 factorial. For example, 12 times 11 times 10 times 9 factorial. I can cancel out the 9 factorials, and that will give us with 220. Simplifying algebraic factorial expressions. N factorial is represented as n times n minus 1, n minus 2, n minus 3, where n belongs to the set of natural numbers. N plus 3 factorial would be n plus 3 times n plus 2 times n plus 1 times n minus 1 times n minus 2, and so on. So if you're reducing or simplifying a factorial expression where we have n plus 2 over n factorial, we have to reduce one in order to cancel with another. And n plus 2 factorial can be n plus 2, n plus 1, and then the rest could be n factorial. And we could cancel these. And we're left with n plus 2 times n minus n plus 1, which will be, in multiplying binomials, n squared plus n plus 2n plus 1. N squared plus 3n, plus 2. Plus 2. Let's look at another example. You have n plus 3, n plus 2, n plus 1 factorial, all over n plus 1 factorial. You see, we could cancel these out. We're left with n plus 3 times n plus 2. When we use a method of multiplying binomials, we get n squared plus 2n plus 3n plus 6, which is n squared plus 5n plus 6. If you would like, you can pause the video now. Try this one on your own. I will continue with the solution. N plus 1 times n minus 1 factorial, all over n minus 1 factorial. Once again, we can cancel out the n minus 1 factorial, and that would leave us with n squared plus n. Undefined factorials. Once again, a factorial is a concise representation of a product of consecutive descending natural numbers. 4 factorial is defined. It would be 4 times 3 times 2 times 1. 0.5 factorial is not defined, since 0.5 is not a natural number. 1/4 factorial is not defined, since 1/4 is not a natural number. Similarly, -3 factorial is also not defined. Yet, 0 factorial is defined, and we must remember and keep in mind that 0 factorial is 1. So in summary, a permutation is an arrangement of distinguishable objects in a definite order. In this case, order matters. A factorial expression can represent the number of permutations of a set of n different objects, that is n factorial, where n must be a natural number.